Chapter 6 of Is Mars Habitable? This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Is Mars Habitable? By Albert Russel Wallace. Chapter 6. A New Estimate of the Temperature of Mars. When we are presented with a complex problem depending on a great number of imperfectly ascertained data, we may often check the results thus obtained with the comparison of cases which in some of the more important of these data are identical, while others are at a maximum or a minimum. In the present case, we can only do this by a consideration of the Moon as compared with the Earth and with Mars. Langley's determination of the Moon's temperature. In the Moon, we see conditions that prevail in Mars, both exaggerated and simplified. Mars has a very scanty atmosphere, the Moon none at all. Or if there is one, it is so excessively scanty that the most refined observations have not detected it. All the complications arising from the possible nature of the atmosphere and its complex effects upon reflection, absorption, and radiation are thus eliminated. The mean distance of the Moon from the Sun being identical with that of the Earth, the total amount of heat intercepted must also be identical. Only in this case, the whole of it reaches the surface instead of 1/4 only, according to Mr. Lowell's estimate for the Earth. Now, by the most refined observations with his bolometer, Mr. Langley was able to determine the temperature of the Moon's surface exposed to undimmed sunshine for 14 days altogether. And he found that even in the portion of it on which the sun was shining almost vertically, the temperature rarely rose above the freezing point of water. However extraordinary this result may seem, it is really a striking confirmation of the accuracy of the general laws determining temperature which I have endeavored to explain in the preceding chapter. For the same surface, which has had 14 days of sunshine, has also had preceding 14 days of darkness, during which the heat which it had accumulated in its surface layers would have been lost by free radiation into stellar space. It thus acquires during its day a maximum temperature of only 491 degrees Fahrenheit absolute, while its minimum after 14 days continuous radiation must be very low and is, with much reason, supposed to approach the absolute zero. Rapid loss of heat by radiation on the Earth. In order better to comprehend what this minimum may be under extreme conditions, it will be useful to take note of the effects it already produces on the Earth in places where the conditions are nearest to those existing on the Moon or on Mars. Though never quite equaling or even approaching very near them, it is in our great desert regions, and especially on high plateaux, that extreme aridity prevails, and it is in such districts that the differences between day and night temperatures reach their maximum. It is stated by geographers that in parts of the Great Sahara the surface temperature is sometimes 150 degrees Fahrenheit, while during the night it falls nearly or quite to the freezing point, a difference of 118 degrees in little more than 12 hours. See footnote 10. In the high desert plains of Central Asia, the extremes are said to be even greater. See footnote 11. Again, in his Universal Geography, Reckless states that in the Armenian highlands the thermometer oscillates between 13 degrees Fahrenheit and 112 degrees Fahrenheit. We may therefore, without any fear of exaggeration, take it as proved that a fall of 100 degrees Fahrenheit in 12 or 15 hours not unfrequently occurs where there is a very dry and clear atmosphere permitting continuous insolation by day and rapid radiation by night. Now, as it is admitted that our dense atmosphere, however dry and clear, absorbs and reflects some considerable portion of the solar heat, we shall certainly underestimate the radiation from the Moon's surface during its long night if we take as the basis of our calculation a lowering of temperature amounting to 100 degrees Fahrenheit during 12 hours, as not unfrequently occurs with us. Using these data, with Stephan's law of decrease of radiation as the fourth power of the temperature, a mathematical friend finds that the temperature of the moon's surface will be reduced during the lunar night to nearly 200 degrees Fahrenheit absolute, equal to minus 258 degrees Fahrenheit. More rapid loss of heat by the moon. Although such a calculation as the above may afford us a good approximation to the rate of loss of heat by Mars with its very scanty atmosphere, we have now good evidence that in the case of the moon the loss is much more rapid. Two independent workers have investigated the subject with very accordant results. Dr. Bodecker, with Lord Rosse's 3-foot reflector and a thermopile to measure the heat, and Mr. Frank Very, with a glass reflector of 12 inches in diameter and the bolometer invented by Mr. Langley. The very striking and unexpected fact in which these observers agree is the sudden disappearance of much of the stored up heat during the comparatively short duration of a total eclipse of the moon. Less than 2 hours of complete darkness and about twice that period of partial obscuration. Dr. Bodecker was unable to detect any appreciable heat at the period of greatest obscuration, but owing to the extreme sensitiveness of the bolometer, Mr. Very ascertained that those parts of the surface which had been longest in shadow still emitted heat to the amount of 1% of the heat to be expected from the full moon. This, however, is the amount of radiation registered by the bolometer. And to get the temperature of the radiating surface, we must apply Stephan's law of the fourth power. Hence the temperature of the moon's dark surface will be the fourth root of 1 over 100, equivalent to 1 over 3.2 of the highest temperature, which would be taken at the freezing point of 491 degrees Fahrenheit absolute, or 154 degrees Fahrenheit absolute, just below the liquefaction point of air. This is about 50 degrees lower than the amount found by calculation from a most rapid radiation, and this amount is produced in a few hours. It is not too much to expect that when continued for more than 2 weeks, the lunar night, it might reach a temperature sufficient to liquefy hydrogen, 60 degrees Fahrenheit absolute, or perhaps even below it. Theory of the moon's origin. This extremely rapid loss of heat by radiation, at first sight so improbable as to be almost incredible, may perhaps be to some extent explained by the physical constitution of the moon's surface, which, from a theoretical point of view, does not appear to have received the attention it deserves. It is clear that our satellite has long been subjected to volcanic eruptions over its whole visible face, and these have evidently been of an explosive nature, so as to build up the very lofty cones and craters, as well as thousands of smaller ones which, owing to the absence of any degrading or denuding agencies, have remained piled up as they were first formed. This highly volcanic structure can, I think, be well explained by an origin such as that attributed to it by Sir George Darwin, and which has been so well described by Sir Robert Ball in his small volume Time and Tide. These astronomers adduce strong evidence that the earth once rotated so rapidly that the equatorial protuberance was almost at the point of separation from the planet as a ring. Before this occurred, however, the tension was so great that one large portion of the protuberance, where it was weakest, broke away and began to move around the earth at some considerable distance from it. As about 1/50th of the bulk of the earth thus escaped, it must have consisted of a considerable portion of the solid crust and a much larger quantity of the liquid or semi-liquid interior, together with a proportionate amount of the gases which we know formed and still form an important part of the earth's substance. As the surface layers of the earth must have been the lightest, they would necessarily, when broken up by the gigantic convulsion, have come together to form the exterior of the new satellite, and soon be adjusted by the forces of gravity and tidal disturbance into a more or less irregular spheroidal form, all of whose interstices and cavities would be filled up and connected together by the liquid or semi-liquid mass forced up between them.